After last week, Mr. Loges had conducted a webinar topic of ultrasound concrete testing, which is mainly on UPV tests. So to continue this, we will learn together today on ultrasound Pulse-Echo method. This Friday, same time, we will discuss the application of ultrasound Pulse-Echo method. We already have many interests in structural safety, durability, and performance, right? So we need an efficient system for early or regular structural assessment, as well as quality assurance. So as one of the most popular and best solutions for detecting flaws in concrete, I think ultrasound Pulse-Echo methods to be considered for your first choice. I should consider or apply this kind of testing for not only new construction, but also for existing buildings. So we can have a quick look on Friday topic over here.
So yeah, just going to run through quickly the main theory, ultrasonic pulse velocity and ultrasonic pulse-echo. 2017, this was Proceq's portfolio. At that time we had the P200 with the dry point contact shear wave transducers were introduced. We also introduced Pundit Live Array Pro at that time. In 2019, we did a major update, which was the Pundit PE200. Pulse velocity theory, it's a simple procedure. We just transmit a signal from one side, we receive it at the other side, and we measure the transmission time. And then based on the distance, we can calculate the pulse velocity. Ideally, for this test, you have to have access from two sides. Pulse-Echo, on the other hand, we have access from a single time, so we transmit and receive on the same side. And then the pulse velocity is 2 times the distance, because it has to travel there and back. So if we know the pulse velocity, we can measure the thickness. We can detect the back wall directly if there's no object anywhere. You can see the signal's a lot bigger. These are typical A scans. Or if we have a delamination, we'll see an A scan echo like that. In this case, we don't see the back wall. There are actually 2 types of waves: P waves, which are compression waves. Particles vibrate in the direction of travel, and we have shear waves, where the particle vibrations perpendicular to the direction of travel. The P waves, they travel much faster, so about typically close to twice the speed of the S wave. And in the past, this was what made S waves difficult to detect. But it's the S waves that we use for pulse-echo technology. And when we're looking at concrete imaging, tomography. So basically we use some kind of a penetrating wave to create slices through slices of the object. We put these slices together to create nowadays complete 3D images. So that's what we're talking about, tomography. This is actually the standardized terminology. The A scan, this is basically the amplitude recorded against the time. And this is the building block of all of our imaging systems, whether it be Pulse-Echo or GPR is the same. We have an A scan like this. If we collect A scans in a slice, this is what we call a B scan. So we create a lot of A scans together, sample them, and we get a B scan, which is a slice through the object in the scan direction. And basically you get an image like this. Reflection at boundaries. For any kind of transmitted wave, you typically get reflections at boundaries. And this is what allows us to create the images. The amount of energy that's reflected is based on the acoustic impedance of the material. So when we have 2 materials, and we know the acoustic impedance, we can determine the reflection. It's quite a simple equation, but looking at the typical materials we have in concrete, which can be air, steel, I mean the other thing you get sometimes plastic, conduits, things like this, and you can see the type of energy that's reflected. So a concrete air reflection, we have almost 100% reflection. A concrete steel, it depends on the type of steel and the quality of the concrete, but it can be like 40 to 50% reflected energy. How we convert the A scan into an image which is more easy to understand, we do it with color coding. So you can see here that we sample the A scan, and we assign a color code to the amplitude. So a red amplitude here, red indicates the highest amplitude, blue indicates the lowest amplitude. And this method allows us to create images which are much easier to interpret. There are the other similar application which covers, similar technology which covers the same application area is impact echo, but it's much more difficult to interpret the signals. Here you get a real visual indication which is much easier for anyone to interpret. You'll see in our portfolio we have single and multiple channel solutions. The Pundit PD8000, it's an 8-channel device. Each row is 3 transducers. Basically this is just to give us some signal level. It's also, we don't necessarily have to have all of the transducers contacting the surface, and we still get transmission, because concrete surfaces can be quite rough. So that's how the 8-channel device works. The principle is like this: 1 channel transmit and the other 7 receive, and then it cycles to the next channel. That one transmits and the others receive, and it runs through this whole cycle in a matter of milliseconds, much faster than you saw there. Basically, as soon as you touch the transducer to the surface, you see the image, and you see it in real time. And the Proceq instrument, it's still the only instrument worldwide that actually does this, to have this real-time image. So you can actually allows you to have a quick look around without actually having to record or save any data. You can get an idea of the structure before you can locate an area of interest without having to record any data, and then start doing more detailed scans where you see there's an issue. And I say it's the only instrument, still it's the only instrument that allows you to do this worldwide. It's unique. So that's actually what it looks like when you see all of the scans that have taken place. It's 128 separate A scans are collected in milliseconds. We can connect 2 instruments together, modular, to create 16 channels. In theory, we could connect more together, but you know, then you have issues with processing power and also the length of people's arms and the weight. So 16 channels is manageable. More than that, it's a bit different. But it gives us some advantages in the range, and also, you know, how quickly you can scan an object. We also, and this was actually the first instrument we released, I think was in 2013, was the single channel solution. This was our entry point into Pulse-Echo testing. It's a very lightweight unit, connects to the Pundit 200 platform, and you can see we have one side is a transmitter and one side is a receiver. And actually it still works very well, and you get very good images with it, but it's much more time consuming to generate detailed images. What it does have, it has automatic slab thickness, so it detects exactly where the echo is taking place. So you can see here's a typical echo trace, and it has an algorithm inside to detect which is the backwall echo, and this is used for thickness measurements. There's also some technology inside for creating clearer images. So we rectify the image first and then create the envelope. And this allows us also to generate better images. Time gain compensation. This is actually a technique which has become more and more relevant as we're able to scan deeper and deeper. Basically, it amplifies images, echoes which are further away from the receiver. If you've got a very deep back wall, and nowadays we can, I mean, the deepest object that I've personally have measured was 1.9 meters, was a motorway pillar. And you can imagine the signal at 2 meters depth can be quite weak. If I try to amplify that and everything else before it, you get a lot of saturation from near surface objects. The TGC allows us to amplify objects which are deeper, while not amplifying objects which are closer to the surface to get a balanced image. Synthetic aperture focusing technique. This is actually what allows us to create clear images. It's, for those who are familiar with GPR, it's analogous to the migration technique in GPR. Basically, a signal, it doesn't travel in a straight line, it actually spreads out in a hemisphere. So when we go past an object like this pipe here, we already start to detect the first reflections when we're some way from the pipe, and as we move closer, the path length gets shorter, and then it starts to go longer again, and then you get this parabolic thing. This is something you'll know from GPR. It's exactly the same concept, and basically the SAFT algorithm in Pulse-Echo technology compensates for this. We know the point in this on the parabola which is closest to the surface, so there we can assume we're directly over the object. And then basically what it does, it compensates for the path length, and it compensates for the distance away from the center point, and basically brings everything together and gives us a sharpened image. And that's like a simplified explanation of what the SAFT does. If you look at an example here, this is actually a scan without SAFT. And if you apply the SAFT, actually the Pundit 200 software allowed you to switch SAFT on and off. With the PD 8000, we always have the SAFT on. If you want an image for that without SAFT, you have to actually use the Pundit Vision software that allows you to switch SAFT on and off. But if I apply the SAFT to this image, then you'll see what happens. It basically sharpens up the image, and you can see here we've got like a stepped object with some pipes in it. And that's actually what the object looks like. This is a famous test block located at the BAM workshop in Berlin. And you can see then how that relates to the SAFT image. Rebars, we've seen, steel reflects 40 to 50% of the signal. So of course it has an effect on the images. You may want to detect rebars, you may want to avoid rebars. You can see here the scan is actually passing perpendicular to the rebars and avoiding the rebar that's parallel to the scan direction. And we get, I would say, quite a strong backwall echo, both from the part without the rebars and with the rebars. You see what happens if we scan directly over a rebar. The second half of the scan, which is directly over a rebar, is much less strong there. So you have to be aware of rebars. It may be that you want to detect them, and nowadays with the new technology, the high frequencies, we can actually detect rebars a lot better with Pulse-Echo than we could in the past. Although I would say it's still not the ideal technology for rebar detection. There are much better technologies for that, and I'm sure Augustine will say something about that later. The type of objects that it's typically used to work on are basically slabs, or plate elements they call them. It's similar it's similar impact echo. Impact echo also defines this type of object. The reason being that when we send a signal out, we get a reflection from the back wall. But as I said, the signal spreads out everywhere. So you also get reflections from side walls. And if this aspect ratio, they call it, if it's a slab, then reflections from the side wall arrive much, much later and much weaker than a back wall echo. But you can imagine if I measure from the side here, then the reflections from the side walls basically blank out everything back wall echoes. So ideally, it's used for testing on slabs, and not like from the top of a column, for example. Ultrasonic Pulse-Echo and GPR. Basically, these are complementary technologies, and it's something that Proceq have been trying to push home this message for a long time now, because we actually manufacture both. There's not one technology that can measure every type of object you have inside the concrete, and it's important to understand that. If we're looking at reflections from steel, with GPR, basically we get a total reflection from steel, but it doesn't pass beyond that. So it actually makes it very good for detecting steel, so very good for detecting a rebar network. But if the rebars are too dense, then it's difficult to see anything behind it. With Pulse-Echo, we get a partial reflection from the steel. It's so basically means it's not as good at detecting steel, but it's better at seeing beyond steel. So if I have dense rebars, I can still detect things like tendon ducts, voids, etc. beyond the rebar layer. When it comes to the air boundary, it's completely the opposite picture. GPR, basically get a partial reflection. It's not so good at detecting objects with air. Large voids, it can detect things like delaminations, it doesn't see at all. This also has to do with the wavelength. But with Pulse-Echo, we get basically a total reflection from air. So any kind of defect inside the concrete which has an air component in it, then Pulse-Echo is the ideal technology for detecting this. And here you can see the three major technologies which we use for imaging inside concrete. So eddy current, this is our profilometer instrument. This gives the most accurate cover readings, and that's actually what it's ideal for. It's you're talking about cover measurements accurate to plus or minus 1-2 millimeters. GPR cover measurements, you're talking plus or minus 5 millimeters typically. So a lot less accurate for that, but very good for detecting rebar structure. Non-metallic objects, of course, below the rebars, so pipes, conduits, anything like this, and back walls down to a certain depth. I mean, we're typically looking at 60-70 centimeters with our GPR, which is much deeper than any, I would say, competitor GPR with a similar resolution. Ultrasonic, we can detect back walls much deeper. I say personally the deepest object I've measured is 1.9 meters. I've also measured on like a 90 centimeter wall and had a third back wall echo, so this like corresponds to 2.7 meters, but this depends always on the concrete quality and how much steel's there. It's the ideal technology for detecting defects, so voids, honeycomb, delaminations. Ultrasonic is the best for this. And say deeper objects, we can go much deeper than we can with GPR. This is a scan. I'm not sure, I think Augustine created this scan, or one of his customers. It's a big, huge test object that they had. If you look at the objects on the left, the Pulse-Echo here is much better at detecting these deeper lying hollow objects. They can both technologies actually detect these voids, because they're actually quite large voids. But on the far right hand side, there's actually a delamination there, and this is much easier to pick up this type of defect with Pulse-Echo. quite often this type of object is invisible with GPR, and that actually shows you how it's a good idea how these technologies are complementary. So yeah, basically that's it. We have a comprehensive solution for this. Feature location, so rebars, pipes, conduits, etc. GPRs, definitely the right technology. For flow detection, Pulse-Echo is the right technology. And I think with that, I can hand it back to Augustine.
I would like to share my screen. I will take an example how to use the instrument, how to look at the 3D image, all this like just a short view. So we have this very advanced iOS app. If you have an iPad, you actually can download the app to your iPad, right? Then look at some demo file we already built inside the app. I just open a previous work. So you should look at this image. We can just simply swap your two fingers on the iPad, right? And you can look at the B scan view, including the A scan information. You can do your tagging, find the certain object location. So actually for this example, we test on a test block, which we built in Switzerland for work of concrete. It's a very complex text block, including very close to surface, there's a PVC pipe, and later on there's a rebar mesh. Under rebar mesh is a post-tensioning cable, and most important, there's a two concrete thickness. So right away, the post-tensioning cable is a thinner thickness, about 300. And later, there's a very thick thickness, about 500 millimeters. So we can look at this one. There's a result. So you can see there's a circular shape. There's a PVC pipe, small conduit. And later on, there's a post-tensioning cable. First, I see there's a first reflection, a strong reflection from the first back wall, and later there's a thicker back wall reflection. So you can just wrap your finger. You will have all the information, right, in a 3D view. So if you feel this result is good, then you can share this result. I'd like to share this result in real time to everybody, right? So I will copy this link to our group chat. So if later on you can feel free, just click the link, open the result and look at how the result looks like. So over here, I want to highlight, we are not only provide this kind of on-site imaging, we also give you a most efficient and most simple way to share your data to create your report. So from here, some people looking at, first will ask us, what's a UPE? So now we have a piece of clear information. It's something good to see defect in concrete. We will talk about this kind of UPE skills, testing skill and function. So how to do it? First, we always touch on this kind of NDT survey or NDT testing. So all these kind of tests are, first we have to base on the set condition and valuable information, for example, drawings, and we can process for to set up our plan, to set up our survey, design our survey. So after we can process the next section, for example, choosing the right instrument, maybe we can go for GPR first, followed by Pulse-Echo test. Then we will perform the proper set testing, is very important. After all the data collected, we conduct imaging, we interpret the data for submitting report. Of course, and we need to give some recommendation. So how to do that? I will mainly focus on the number 3, some best practice on Pulse-Echo testing. So before that, when we go ahead for concrete testing with ultrasound Pulse-Echo, we should understand some preset parameter and how to calibrate the velocity. It's very important. It's a key for success UPE data collection. So this including something like first we need to choose whether we just set up a line scan for 2D image or we need to set up a 3D scan. So first thing we need to calibrate our velocity. Keep in mind, it's very important. So same as a GPR, we need to calibrate the radar wave speed as well, based on the material dielectric constant. And here we need to base on the material, this kind of different shear wave traveling speed. We can calibrate the velocity, and then we can have an accurate depth detection. So first topic, let's look at this velocity calibration and during offset. There's a short video to show you how to do a double echo calibration with a system in just 10 seconds. So once you find the two echoes with no in-depth, you can put the second echo cursor with object tagging, right? So after you can measure the total depth and input the total depth. So everything is done. So in this way, you can calibrate the material velocity and the signal zero offset together. We can look at a real case example. This is the same test plot just now I show you. This after proper calibration. Basically, we use a double echo based on the thicker thickness, which is 500 millimeter. So this is the end result. We can look at individual objects. For example, top we have a delamation at 150. You can see the real result we get about 149. At least a smaller depth at 300, we have a 295. I'd like to say, if you have a proper calibration, the depth calibration can be minimized less than 2%, right? It's quite accurate with this kind of ultrasound Pulse-Echo method. So once you have the final image, you can look at how the object and is how accurate with this ultrasound Pulse-Echo method. And recently we introduced this macro view to our new system. So this macro view provides you optimized transmission parameter settings and really reduce your preset process. So there's a lot of time consuming when we're doing preset. So if you activate this new function, it really help you for your ultrasound Pulse-Echo method. There are three total different kind of setting. First is an intermediate field. If we're looking at the depth around 1 to 1.5 meters, you should use this default setting. So basically we use 40 kilohertz, this center frequency, transmitter voltage at 100 volt, maximum transmitting time at 100 milliseconds. So next one is a near field. If we're looking for first layer or second layer, this kind of rebar detection on shallower depth, we should keep this near field settings. So you can look at this setting, we use a higher frequency. As you know, higher frequency with a shorter wavelength, basically give you a clear resolution. Come to voltage and transmitting time compared to intermediate field is halfway, right? And next one, we have a far field, basically for large object. Typically can cover 2 to 2.4 meters, this kind of penetration. It very depends on the material you test. We use a lower frequency. Basically, lower frequency has a less signal attenuation, and we have a better this kind of signal penetration. So this is a very basic three macro view. Before you test, you should always turn on this function. Just now, Dave already mentioned the sub function. So in the past, we know sub function actually has some disadvantage because the set of the image is distorted. So we try to forbid this kind of distortion during the image collection. we can use this kind of a simple image stitching, right? So this stitching method allows the B scan to overlap to next one with certain portion. So we suggest at least one channel overlapping, right? So for some cases, if you want to achieve a better image, so you need to overlap maybe 2 channels or more channels. Over here, one channel means from one channel to another traducer, there's a distance. So from the image, you can see this one channel give you a distance about 3 cm, right? So one image, and next image is overlap with one channel. We can look at a real case over here. This test we did in Switzerland office, car park basement. I trust the digger wall is a retaining wall. The right hand side, this thinner wall actually come from near to entrance. So for this test, quite interesting. We can look at 2 different penetration depth. So this test result actually finished in a couple of minutes. They use 2 channel overlapping, means from one image to another image, there's a 6 cm overlapping. So this is another very useful testing skill during the preset. You can preset how much you want to overlap. So you have to, based on your survey design, think over your productivity, right? We have this new function we call artificial intelligent positioning system. I call this tape is an AI tape. For this Pundit 8000 traducer has an onboard camera which can automatically recognize this AI tape. You can test both horizontally and vertically. Each tape is about 1.5 meters, so we can continuously paste a tape on the testing surface for up to 10 pieces. So we can look at this video. We place 2 tapes on the testing object, so we can cover 3 meters. So what we do when we come to 1.5 meter finish on the first measurement, so we just swap on the iPad screen, come to the second screen. So the good thing when you capture any image, you don't need to care the sequence you measure. The system will recognize your position automatically. So we can go for up to 10 meters, means you can cover about 15 meters in a line scan. So this is a way how we conduct vertical scan with this AI tape. So we can use this way, we call strap scan. We can easily conduct a 3D view later, which is, I shared the image just now, exactly the same measurement we did, and come with 16 channel measurement. We also encounter a lot instability during the image collection. So this test result, I do a screen record during the CTE tunnel inspection. We have the client do some tests. During the data collection, we can see a clear first 2 images. We have a total backwall about 1.1 to 1.2 meters. So you can see this instrument can really go very deep. So next, we can look at how the screen recording looks like. So you can see the A scan, which is at your left-hand side, is very unstable. The reason behind is due to the overhead tunnel location is just under the expressway. So there's many vehicles pass through during our data collection. We know UPE is kind of direct contact testing, right? It uses a mechanical wave. So any background resonant energy will greatly affect the stability of real-time B-scan image. So what's the solution behind? Look at our stabilizer. So during data collection, you can pre-activate this image stabilizer. It's a great function to make your real-time image smoother and easy on your eye, I'd like to say. So all these preset parameters you can see another we amplify the stabilizer, your image almost freeze, right? And there's no background influence from behind. So all these preset parameters, including just now we introduced stitching your image, calibrate the velocity, zero offset your signal, macro view, use the AI tape for AI positioning, and lastly is image stabilizer. So all this one during preset, we have to optimize our image. Come to data collection, we always need to wisely tune our gain, right? To tune our gain, we can have a better 2D or 3D image. There's a few gain functions. I may not give more details over here. So first gain function we call analog gain. Also we call total gain. Means you enlarge the gain function, it will go up and down all along the transmission line. All this A scan will be amplified, right? We also have a TGC function. TGC function, which is amplify the further field, and you can look at the further field object as clear as the near field. Over here, I want to emphasize some AI function, which we can automatically detect the backwall, and later some image function for Proceq data and reporting. So first video, you can look at how we detect a backwall with this built-in app function we call automatic AI backwall detection. We take a few scans on this small wall, about 25 cm. First, you just put your focus box, which roughly is your focus area. Go to menu, select the tape. And there's a function called AI tagging. So you can see all these two tags is automatically assigned by the software itself. Dave also mentioned a very interesting function. We know GPR is very good for detecting metallic object. Ultrasound possible to detect a metallic object. So we have some new correction on the previous sub function. We call it high definition focus. And this correction allows you to apply the depth from 0 to 50 cm to correct the automatic sub function. So we can look at this video. So actually, there's two rebars left and right, and there's an actual location after the sub function active, a new function activate. We can look again. So this raw data which we can't recognize the two rebar. As long as we activate the new high definition focus, these two rebar become visible. We collect this data during the Taiwan visit, right? Strong, our Taiwan concrete partner, provide this data. So we can look at how this kind of example of how useful for this high definition focus. If you don't turn on this function, you will not see, especially at right hand side, this two rebar, right? If you just turn on, the image was adjusted, these two rebar become visible. Let's have a closer look, like a different view. For example, when we set up a strap scan, we can easily have a different depth view. We call time slice. We can look at different depth, or we can have a black and white color 3D view. If you're Pundit PD8000 user with a pro version, you can have this 3D color view. And lastly, if you have a pro version, you also can project your image on the test object, right? Of course, you can use this AR function for many uses. For example, you can set up a Zoom meeting, have an interaction with some expert on the spot after your test. You can have some on-site visibility for this kind of collaboration. And in some training school, they also use this kind of lab solution from Proceq. Use a lab device, just set up the online training courses for NDT. Before move on, I would like to share some information, right? for this AR, I'd like to do a live demo over here. Then we can continue with some case study. So you can see we can right away project the image. So I will use the same image and just project on my floor and my room. So you can see how useful for this function. So you can see I actually take out this data. Also, I just scan the map. Okay, so I should flip the map. So this is our AR function on the screen. So after scan is GPR scan map exactly the same. So I can easily project the image on my floor, right? So I can take out the object and look at. Also can do some different depth view. For example, from surface, I have this small PVC pipe, like a curvature, and this light blue color, that's a post-tensioning cable. And later on, this blue color, that's first back wall at 300 mm. And next one is a bigger back wall at 500. So you can see if I have a Zoom meeting with this kind of visibility, we can easily solve a lot on-site issue in real time. I'd like to share some case study. Basically, this some case study we only use for our master training. So in future, anyone interested our master training on advanced NDT method, please contact us, including both GPR and ultrasound Pulse-Echo method. From previous slides, we already understand our Pundit system is aggregable. For example, for Pundit PL200 single channel PE unit, you can upgrade to multi-channel Pundit 250 array. Then you can further upgrade to PD8000 basic or pro. Also, you can have an 8-channel or 16-channel. So all this data is collecting on different solutions. First, we can have this is a irregular shaped concrete block, and center has a 4 PVC pipe. AB pipe comes with a diameter around 50 mm, and CD pipe has a diameter around 75 mm. First, we have this single channel solution. I'm not saying single channel is useless, right? It is in some case, like Dave mentioned, it's good for total thickness detection, but in certain range, I'd like to say maximum you can go is around 50 to 80 cm. It depends on the material density. So in this case, we can have a clear information A, B, C, D, right? All the four part is detect, but the back wall is distorted, or I'd like to say is broken. It's not continuous back wall. Next one is a 250 array, our first multi-channel solution. So you can see 1, 2, 3, 4 pipe, very clear back wall, thinner depth at 400, and bigger depth 60 cm. You also can see something. And next one, we move to Pundit 8000 Pro. You can see a clear information on the full back. The image is much more clear compared to previous solution, right? Last one is a 16-channel solution. I'd like to say is because the resolution is much more improved, the test speed also much more improved with these 16 channels. Actually, for this test, you can easily 1, 2, 3 finish less than 4 to 5 seconds, right? Because transducer provide one image scan is about 45 cm, so in this wave. Next one, we have a V-shaped block. Inside we build a honeycomb for stone back, right? So A1, B1 use aggregate size around 20 cm, 10 mm aggregate. A2 and B2 use 25 mm aggregate. So someone is small stone, someone is big stone inside. So we look at a single channel solution here. So we scan crossover on A1 and A2. So the image we can see A1 and A2 also quite clear. And we know most of the signal once bounced to A1 is total reflection. So in this case, mostly you will not see a clear backwall. So next one is a 250 array solution. So we can see A1, B1 is much more clear compared to a single channel solution. And most important, you can greatly save your time. We have a lot of Pulse-Echo single channel user in the past, right? They know the pinpoint how to conduct B scan image. For example, in 1 meter scan, you easily cost you 20 minutes or 15 minutes for a very experienced user. Let's look at next, PD8000. So you can see the defect is much more clear. And most important, you can have a set backwall location, right? So next one is a 16 channel solution. The image quality is much more improved, I would like to say. We also can scan, which is the solid position, means in between the two defects, right? So we do a scan in between the defects, at least a single channel solution, at least a multi-channel 250 array. So this direct comparison up and down, you can see image quality is much more improved in our first version multi-channel solution. And importance, this whole measurement can finish in 8 scans, just less than 20 seconds. You can have a direct B scan image. So this was conducted by PD8000 unit, which is a wireless solution. Image quality much more better, including the 16 channel, right? We also use this 16 channel to conduct 3D scan in this same test block. And this test block, we do the scan like a screen show. We cover 1, 2, 3, 4 defects, including the center backwall. And you can look at how the result looks like. So you can see this A1, A2, and B1, B2. I'd like to say B1, I didn't take out too many results because I think during the construction, B1 was broken. From here, you can see only a little bit overlap, right? But the light blue is showing very clear there's a total V6 block at behind. We have one more example, also a training block. It comes with different position rebar with a different size, and we built in 2 delamination in this block. So you can see this single channel solution. We can find the delamination 1 at the center of the block, and delamination 2 are very close to the back wall. And there's 1, 2, 3, 4, 6 rebar at left-hand side. Importance, there's some rebar effect, right? We mentioned before, right? Even we cross a rebar, you can see the back wall is not as clear as without rebar, right? So this, when you're doing the single channel UPE testing, you have to take notes. Rebar location is very important, and try to avoid the rebar as much as possible. Next one, we can look at this Pundit 250 array solution, and we can look at the delamination 1 and delamination 2 is much more clear, right? And the rebar is also clear. Important, your back wall also very clear. The importance when we use a multi-channel is a signal. We use more A scan to contrast with a B scan. So in this way, we have a clearer B scan image, resolution-wise, much more better. We also conduct a PD8000 scan. We use 1, 2, 3, 4, 7 scans. So you can easily, less than 20 seconds, you can have this image. The good thing I want to highlight the high definition focus, how can apply in this case, right? We can look at this short video. So we can see a clear backwall 1, 2, 3. I'm quite confident to assign this one as a rebar, but the rest is not so clear. So in this way, we turn on the high definition focus. So we can have this rebar on the display. Lastly, I have like to give some input on our latest update. First one is Pundit Vision. It's a very powerful PC software to analyze your UPE data. For example, some data you collected, you can download to PC and use this powerful PC software to reconstruct a 2D or 3D image. Next one, I'd like to highlight the difference between all the different multi-channel solutions, right? So we can look at Pundit 250 array and Pundit PDA1000. Most or less for cloud feature, we don't have any function on Pundit 250 array, and mainly is on Pundit Pro. And we know this function, there's a new function called HTML data export. Begin my presentation, I already do this. So you can use this link I share to you and open and look at how this data I share to you. So this is a new function over here. When we design our NDT survey, we have to look at what kind of function, what kind of visibility we need to apply to our project. So all this one, we have a quick introduction today. Please think wisely, choose your best solution from Proceq. So that's all from my side as end of today's presentation.
This question is from Mr. Nitin Kumar. I think he is asking what is the minimum size of defect that our instruments can detect easily.
I mean, generally the rule of thumb is like half a wavelength, and at the typical frequency that we're operating, that's you're talking about 2 centimeters. But I mean, testing we've done with, and it was actually an Indian Technical University in Berlin, we know we can see, for example, even 10mm rebars now with the high definition focus function. So yeah, I mean, definitely object sort of voids, you're talking about typically sort of the size of a table tennis ball, gets quite difficult to see with real precision. Voids the size of a tennis ball you can see, but I say we can detect smaller objects. Rebars, definitely we can detect much smaller size rebars.
You can answer one last question. Can we detect hairline crack?
You can detect it if it's more or less parallel to the surface. That's what we call a delamination. It doesn't matter how thick it is. So even if it's a hairline crack, we detect it, we get a total reflection. And this is actually something you can only detect with Pulse-Echo. GPR would be blind to that. Cracks going down vertically from the surface, this we can't detect. But if they're more or less parallel to the surface, then we can detect it.
And also from Mr. Nagesh, can our Pundit technology be used on rocks for maybe the depth sizing, the depth measurement, or maybe also crack detection in the rocks?
Absolute 100%. We have an application in Italy where they use it for doing quality control on marble blocks for crack detection, things like this. Similar to like testing on concrete, of course you don't have rebars or anything inside. So definitely for testing on rock slabs and cracks, it is being used. For testing on massive rock, the difficulty there is that there's quite often no reflector inside for it so you don't really see anything. I've used it on tunnel walls where we've actually had shotcrete on top of it. But like I say, on slabs, rock slabs, things like this, you can use it, and you can use it to detect cracks. There's actually, I've even posted some videos on LinkedIn about this.
And another question from Indradi, the last question. What is the minimum distance between rebars, the minimum distance between the rebars that we can detect to identify each individual?
I would like to answer this question. So next webinar, we are open some application notes, especially for PDA1000. There's a real case study, which is a 2 rebar at shallower distance overlap. So we can see the two rebar is very clear. I'd like to say this test method in some situation can be better than GPR, this kind of rebar detection.